specifically the compressor story. And so what this is going to be all about is we're going to talk about the different compressor technologies, and we're going to talk about why we choose one particular compressor over another compressor and so on. So it's just basically a good basic overview of compressors, how they work, and more specifically, why Johnson Controls, unlike some of our competitors, they may try to squeeze one compressor technology into their entire product line. We don't do that. And so we're going to kind of talk a little bit about that as well. And so at this time, I'm going to go ahead and now, Emily, are we recording at this time, you said?
We are.
Okay. So I'm going to go ahead and shut my camera off because it normally streams a little bit better when I shut my camera off. And Jessica and Emily, if you guys will kind of be the scribes a little bit, if we see anything in the chat, just let me know. And let me share my screen at this time. And let's see here. And then we'll make sure everyone can see the screen okay as well, as we kind of open up the old slideshow. And so everyone should be on, we should be on my main screen, your champion product, and some pictures of some product. Is that correct?
That is correct. Okay.
Well, let's go ahead and jump into this. So basically, again, this is going to be a compressor technology overview as we talk about the different types of compressors that we have in our product lineup. And based on the tonnage and based on the SEER rating and based on the type of product it is, you may see a scroll compressor, which we see on the left-hand side. You may still see some recip compressors, which you see in the middle. And on the right-hand side, you'll notice that there's a rotary compressor. They all look a little bit different. The scroll and the rotary kind of look alike, but they do definitely have different technologies. So this presentation, again, we're going to talk about the different types of compressor technologies and compare their features and performances. In addition, we'll discuss some of the factors, again, that JCI considers when we apply each technology. Now, please remember the function of the compressor in the refrigeration cycle is going to be the same regardless of whatever technology we use. We're going to talk a little bit about compressor construction, some operation, and some of the characteristics as well. So again, it doesn't matter if it's a rotary, it doesn't matter if it's a scroll, it doesn't matter if it's a recip. They're all going to serve the same function in the refrigeration cycle. We'll have a compressor, we'll have some coils, we're going to have expansion valves and so on. None of that changes with the compressor technology. So we're going to really be drilling into the compressor itself today. So as we take a look at the compressor and the function of the compressor, let's dig in a little bit and actually discuss some of the things that the compressor actually does. Did we have a question? Okay. So as we take a look at it, the role of the compressor is to increase temperature and pressure of the refrigerant, and to move that thermal energy from the refrigerant to the outside or to the inside based on if it's in the heating or cooling mode. So the compressor actually circulates refrigerant by creating a pressure differential, pulling in low pressure vapor on the low side and pushing out high pressure vapor on the high side. So as we kind of take a look at that little graphic, we see that from the compressor, we've got hot gas going through the discharge line, through the condenser. It condenses it into a liquid. It goes down through a filter dryer and hits the TXV. From the TXV, it sprays that liquid refrigerant in the evaporator. It boils that refrigerant liquid into a vapor, into a cool vapor. It sucks it back on the suction line back to the compressor. As a matter of fact, when we've talked about that in our basic refrigeration cycle, this is kind of a little overview of that, or a reminder for everyone. But the compressor is kind of the heart of the system. It's really what allows refrigeration effect in both coils as well as circulation through both coils. Now, please remember the compressor motor windings require that cool suction vapor to return in proper amounts or damage will occur. So it's very, very important. Refrigerant flow through that TXV is critical, and we have to make sure that we're properly charged and we have proper airflow. All of those become real important for a strong, reliable system.
So Joel, sometimes you might hear like some of the terminology might be is you're flooding the compressor or you're starving the compressor. Is that what you're talking about when you're talking about getting proper flow?
Yes, that's a good question, Emily. So basically, when we're talking about a flooded compressor, basically, if you've got an overcharge in the system, or if the evaporator is iced up, or if it's filthy, there's no airflow on the evaporator, what will happen, that refrigerant won't have the the ability to boil completely off in the evaporator if we have like low airflow or the fan speed on the indoor coils at the wrong speed, or we have a filthy air filter. As a matter of fact, everyone, you might want to write this down. The number one cause of low suction pressure, if the system is properly charged, the number one cause of low suction pressure and flood back to the compressor is a filthy filter. It's just a filthy air filter. And so that's the number one cause of that flood back, to Emily's good question. And so that's exactly what we're talking about. We have to make sure that we don't slug liquid back to the compressor, but we want to have sufficient suction vapor going back, proper suction vapor going back to cool the compressor windings and to make everything work properly. So airflow is very, very critical when we're talking about that. Good question, Emily. Let's take a look at some compressor construction and basic operations. So on the left-hand side, this is just kind of a little graphic that we're looking at, but on the left-hand side, we see at the upper left-hand side, we see there's two scrolls. There's an orbiting scroll and a fixed scroll in the scroll compressor. Now what happens is the refrigerant comes in where it says inlet port, and as those scrolls orbit around each other, it actually increases the pressure, and then it pushes that high pressure refrigerant vapor right through the center of those scrolls. So the scroll kind of orbits around and kind of screws that refrigerant and increases the pressure. On the right-hand side, the upper right-hand side, we see that's a kind of a little graphic of a rotary compressor. So what happens is the refrigerant comes in, and that rotary compressor, it's kind of an off-center, a cam in the middle, if you will. And so as that refrigerant comes in and it starts to rotate, and it starts squeezing, that cam just kind of squeezes that refrigerant around the outside and then discharges it over there to the left. So if you can kind of imagine an offset bolt or an offset cam inside of a round cylindrical housing, as that cam rotates, it's going to pull that refrigerant in and sweep it around and squeeze it against the walls of that cylinder as it rotates on that concentric, or more specifically, that kind of elliptical path there in the rotary. And then if we take a look at the very bottom graphic, we see the old reciprocating piston compressors. This looks very much like an automotive engine because that's really how it was all kind of designed, I think. It's the same principle. So you see a crankshaft and a connecting rod. And as that connecting rod goes up and down, and as that crankshaft turns, what it's going to do, if you take a look at that reciprocating piston compressor, what happens is we rotate it around. That connecting rod is going to, it's off center on the crankshaft. It's going to impart vertical rotation on that piston as it pumps up and down and up and down. Now, as that piston comes up, it's going to compress that refrigerant and push it out of the discharge valve. And as that piston starts going down, it'll create a vacuum inside that cylinder, and it'll pull refrigerant past the suction valve as it fills that piston and that cylinder assembly up. Then when that piston starts coming around up again, it pushes it out the discharge valve. So if you can kind of imagine how an automobile engine works, and air compressors is very, very similar in the fact that you've got that piston, a connecting rod, and a crankshaft on that reciprocating piston type of compressor. So those are the three basic technologies we're going to see the most of in our industry: scroll compressors, rotary compressors, and reciprocating, also called reciprocating piston compressors. Any questions or comments so far as we take a look at these basic compressor technologies?
So Joel, these are basics. Are there any other types of compressors that might be out there?
There are, but when you start getting into the commercial world and the refrigeration world, we have what we call centrifugal compressors, which are very, very huge. They're almost like just a huge wheel that kind of turns inside of a large housing. And those are called centrifugal compressors. You'll see that in very, very large HVAC application. In addition, in the refrigeration world, we have what we call a screw compressor. So if you can imagine just a large tapered screw, literally just like a big screw, inside of a housing, and as that screw turns and comes up to speed, it actually pulls that refrigerant along those threads, so to speak, in a screw compressor. So yeah, there's different compressor technologies, but from a manufacturing and from a practical standpoint, up to probably 50 or 60 tons of air conditioning capability, you'll never see anything except like a scroll compressors or those types of technologies. You don't start getting into like your centrifugals till you get into like 150 tons, 200 ton air conditioning, and you don't start getting into the screw compressors until you get into some of the big, huge, low temperature ammonia systems. Typically will have a screw type of compressor. Good question.
We also had one in the chat about, what about a tandem compressor?
Okay, so when you talk about a tandem compressor, that's basically a tandem compressor is going to be more than one compressor that's piped in to another compressor. So if we have like two compressors in tandem, they're going to basically share a suction line and a liquid line and so on. So based on the size of the unit, you may even have 4 or 5 compressors kind of all tied together on some of these large units, but typically they'll be like like on a 20-ton unit, you might have 2 10-ton compressors tandem together, or you might have 4 5-ton compressors tandem together. So the word tandem kind of makes me think about, or it makes us think about having more than one compressor tied into the same refrigeration circuit. That is correct. So in commercial world, you'll see that quite a bit.
So if we're just talking residential, we would only really have one of these 3 compressors.
That is correct. That's a good observation. So the scroll compressor lends itself really, really well to single stage and 2-stage operation. The reciprocating compressor lends itself well to just like a single stage application. And the rotary compressor lends itself very well to like variable frequency drive or modulating technologies. As a matter of fact, like our HMH7, which is a 35 to 100% modulating compressor, that is a rotary type of compressor because the rotary lends itself well to that particular technology. Good.
Which we're going to get into, right?
Which we're going to get into a little bit, yeah. Okay, so let's take a little deeper look into the scroll compressor to start out with. So as we take a look at it, you'll see on the left-hand side that picture, that's the 2 scrolls that we're talking about. And they look kind of they look like a scroll. That's the easiest way to describe it. So one of them is fixed, and the other one fits inside of the other. So they mate together and they fit together. And then the motor drives one of the scrolls on a kind of an elliptical plane, if you will. So they sit there and as they spin and they interface with each other. Now, it should be noted the actual scrolls themselves don't touch, but the very, very tip of the scrolls on the very ends, they mate together, and that's where you get a nice seal for your refrigerant. Now, as you take a look at that compressor a little bit deeper, you see we have a suction port where we have that refrigerant coming in and our cool gas coming back from the evaporator. And we have a discharge port. That's where the hot gas or the high temperature and high pressure refrigerant goes to the condenser coil. And then as we take a look at it, as we think about, as that suction port and that low side, what we call the low side, that's all going to be suction pressure on the low side. And then that high side will be the discharge pressure on the high side of that shell or that compressor shell. Now, as we kind of look a little bit deeper, we see that we've got some different components inside. We've got a muffler, a discharge expansion area that acts like a muffler. We've got a fixed and an orbiting scroll. We have some overload devices on the motor. That OLP means overload protection. We've got the motor itself, and then we've got some bearings and some oil down in there and so on as we complete that basic assembly. So basically, we have a totally sealed compressor with 2 scrolls in there that are going to be driven by a motor and a high side and a low side. Any questions or comments on that basic construction of the scroll compressor?
So what is there really a reason why we have a high side or low side, or what is that in reference to?
That's a good question. So remember in our basic refrigeration training, our basic refrigeration cycle, when we have that suction gas coming back to the compressor, that's going to be at a low pressure, typically on 410A, about 130 pounds of suction pressure. And that compressor is going to suck in that low pressure vapor, that cool low pressure vapor, is going to squeeze it and compress it. Well, as we squeeze it and compress it, we've got to do something with that high pressure. And so what we do is we put it through what we call the high side or down the discharge line. So every compressor technology, that's a good question, Emily. Every compressor technology is going to have what we call a low side, where you're going to have suction vapor coming in, that cool suction vapor coming into the compressor, and then it's going to squeeze that refrigerant into a high pressure hot gas. Well, we have to do something with it. So at some point in that compressor, there's going to be a high side and there's going to be a low side within that compressor assembly. Good. Excellent question. Okay, let's have a quick look at some of the strengths and some of the considerations, if you will, for a scroll compressor. Now, some of the real big things about a scroll compressor, because it has a fixed compression ratio, you can really optimize it for a particular tonnage and SEER rating. So what I'm saying is a scroll is very, very good if you really know exactly what your load's going to be and you want to optimize your SEER rating. It does have longer suction and discharge events, which actually result in a lower pulsation and sound level. So scroll compressors, they're relatively quiet within the tonnage ranges because of that. Another thing is they have the very, very high, what we call volumetric efficiency. So volumetric efficiency has to do with how much gas do I suck in compared to how much am I actually compressing. And so when we're talking about that, scrolls really work well. I mean, they're in the upper 90% volumetric efficiency. So let's just say we had a pound of refrigerant sucked in, we're going to pretty much squeeze a pound of refrigerant going out. So that's what that's all about. And because of the compliance, we're talking about compliance mechanisms, it tolerates some slugging fairly well. So the way the scroll's designed, if you do have some slugging or some liquid coming back, like we talked about earlier, if you have like a dirty air filter on your evaporator, you're kind of spiking or you're kind of slugging a little bit of liquid back to the compressor, the scroll compressor actually tolerates that pretty well compared to other technologies. And the neat thing about it is it starts against differential pressure. So unlike a recip compressor, for instance, that doesn't like to start against pressure in the system, the scroll does quite well as far as that. So that means that you have a reduction in the need for hard start kits, for instance. Scroll compressors typically don't need hard start kits, where some other technologies may require a hard start kit. Now, some of the considerations about a scroll, if you will.
Hold on, Joel, 1 second there. I was on mute. So there's a few things I just want to go in clarify just a little bit more. So high volumetric, we would see that more on some of our high tonnages, right? So if it's a smaller unit, it would be lower volume. Higher tonnage would be more of your higher tonnage units.
Yeah,
correct?
So that is correct. So because of that volumetric efficiency, scrolls lend themselves to more efficiency in the higher tonnages. But it also, that the higher volumetric efficiency, it also lends itself well to higher SEER rated equipment. So even though we might have let's say we have a 2-ton, a 17 SEER unit, you're probably going to have a scroll in there because the high volumetric efficiency, the scroll lends itself more readily to a higher SEER rating, but also it performs better in higher tonnages as well. That is correct. Good.
And I think you briefly touched on slugging. So that was kind of like in our instance earlier we talked about where you had your dirty air filter, you weren't getting as much airflow over the coils, so there was some liquid that was coming back where it's typically only supposed to be bringing back vapor, right?
That is correct. So ideally, in a refrigeration circuit, we want to have cool vapor coming back from the evaporator. We don't want to have liquid coming back because that liquid can actually damage the compressor. Because remember, Tame, you can compress a vapor all day long, but you can't compress a liquid. If you try to compress a liquid, it starts mechanically damaging components. And so the way the scrolls design it, it can actually, what we call the compliance mechanism, it actually can tolerate a little bit of liquid slugging.
Very good. And
go ahead.
Oh, go ahead. Oh, I was just going over your strengths just a little bit more in some of the more basic terms. So preferential differential, you talked about hard start kit. If someone doesn't know what a hard start kit is, can you go into kind of what the one of the ways I like to put it is that sometimes when I'm thinking back a little bit older times when you had a unit come on, your lights would flicker in the house.
So a hard start kit will improve that. It's not 100% fix on that, but basically what happens when a compressor shuts down, in other words, when the thermostat is satisfied and the outdoor unit shuts off, what can happen is there's going to be a pressure differential for a while between the high side and the low side, even after the compressor shuts off, until the pressures in the system start to equalize through the different components, like a reversing valve and an expansion valve and so on. So during that time, where it's equalizing those pressures, during that time, we need to let the compressor just set a little while in between cycles. But hang on a second. So let's say, for instance, the thermostat called for cooling 2 minutes after the last cycle. Well, depending on the type of thermostat and depending on the product you're looking at, it may try to start again against that high pressure, that high side on the high side and the low side on the low side. And there's a pressure differential across those scroll plates. So what happens is if you, on some compressor technologies, especially recip compressors, if you have a high pressure differential across that piston, it doesn't like to start. And so we can help alleviate some of that with what we call a hard start kit, which is just an electrical component to help kickstart the motor if it should happen to start before those pressures are equalized. In addition, you'll notice that on our Champion product, all of our Champion product expansion valves, we feature what we call a bleed port expansion valve. And this is getting a little bit deeper than I wanted to today as far as components, but basically we have some other components in our refrigeration cycle, our bleed port expansion valves, for instance, that help overcome that pressure differential in our technologies. So good, yeah. So some quick considerations as far as the scroll plate friction can be fairly high. And so we want to make sure that that cool gas is coming back, and we never ever want to run a scroll compressor in a vacuum, and we never want to run it without refrigerant in there because that can cause some issues. Vibration levels can be a little bit higher based on the tonnage and the application. And because we have a lot of machine surfaces inside, it does take longer, and it does take it's more expensive to actually make a scroll than some of the other technologies. Now, some of the 3D machine surfaces do actually require some advanced tooling and extra quality control. The other thing about a scroll, we do have higher oil circulation rates, which means that it's going to be important that our line sizes are the proper size so that we get good oil return back to the compressor. And compressor stability can be affected by system pressures. Again, we never want to run a scroll compressor in a vacuum because it's just not designed to do that. You can actually overheat the scrolls if you do. And finally, it does require proper refrigerant suction flow to avoid overheating and damage. As we talked about earlier, we never want to run those systems in vacuums because it can cause issues with cooling those windings. And we always want to make sure we have enough flow coming through the evaporator and the expansion valve, and make sure we have good airflow and all, like we said before, to make sure that we've got that cool gas coming back to cool those scrolls on the scroll compressor. So good.
Joel, let's go ahead and talk about that oil. So why would we need oil for a compressor?
Well, that's a good question. So any mechanical component, if you think about it, think about your car. You've got oil in your car crankcase. It's the same thing. At the bottom of that compressor, that's actually almost like a little crankcase down there. You've got bearings down there, and those bearings need to be lubricated. So anytime you have a mechanical device that's rotating or moving and so on, even though it's internal, those bearings are internal, you still have to have oil to them. So that's the big deal. It's very, very important that we have oil in that compressor, and we have to manage that oil too. And again, the big thing about oil management is to make sure you have the proper size line set. Otherwise, you can end up putting all that oil, out in the line set. We have to be able to return that refrigerant oil back to the compressor. And the main thing about that is make sure and watch those line set sizes and recommendations. Okay, good. Good questions. Any other good questions or comments on the chat before we continue?
I haven't seen anything yet, but feel free to go ahead and type in the chat, or go ahead and unmute when you have a question.
Absolutely. Absolutely. Okay. So again, a quick reminder, as tonnage increases, scroll performance increases relative to other technologies. So scrolls are a real champ in the larger tonnages and the higher SEER equipment because of that volumetric efficiency that we talked about earlier.
All right, Joel, we did have another one come in. You talked about muffler on the scroll compressor. Well, can you talk to the reasoning why we would have a muffler?
That's a good question. So anytime we, just as its name implies, a muffler is going to help increase, or I should say decrease sound or objectionable noise. And so a muffler, if you see a muffler on any refrigeration component or any refrigeration system, what it is we're basically trying to quiet that compressor down. And you know, in our testing facilities, in our HALT facilities, our highly accelerated life testing facilities at Johnson Controls, where we test all of these systems and all the different technologies we're talking about, we may have identified on a particular product that we need to have a muffler to help attenuate, or more specifically quiet, some of those sounds on the refrigerant flow as well as the compressor itself. So that's all the muffler does. It just, like a muffler on a car, it just kind of quiets things down a little bit.
And I guess while we're talking about that vibration, have you seen instances where vibration can travel through the line set?
It can. And again, so this is a very high level of comment. But you know, when we test, when we do all the testing and development of a product at Johnson Controls, so we'll take a compressor technology and we'll test it. We'll build systems up. We'll run it through the test lab and the sound lab and the vibration labs and so on. And we actually design and build the piping in that outdoor unit to augment that sound or augment that vibration. So in other words, if we identify a vibration issue in a line set, we might put a bend in that line, or we might put like an S bend or a U bend in a line to get away from that vibration. So yeah, we do a lot with line sizing inside the unit itself to help you know, eliminate or certainly greatly reduce vibration and sound and stuff like that, you know, in the outdoor unit. So good. All right, so let's talk a little bit about the recip. The recip compressor team has been around a long time. It's actually one of the oldest technologies. As you can see on the right-hand side there, you've got a piston that's actually going to be moving up and down in a cylinder. Again, very much like an automobile. But as we take a look at that compressor, here we go. We've got a suction port again where the cool gas is going to come back from the evaporator in the refrigeration cycle. And we've got a discharge port where the high pressure hot gas is going to go to the condenser coil. And so the entire, on a reciprocating compressor, the entire shell is actually suction pressure, or what we call the low side. So the entire shell is going to have this cool gas coming in to cool the motor windings and to cool the compressor and the whole 9 yards. That the entire shell there is going to be low side and subject to that cool gas coming back on the evaporator. Now internally, there's going to be a discharge tube, and you can kind of see the cutaway there a little bit, but that discharge tube is going to allow that hot gas to go internally, isolated internally, and then out the discharge port. So that discharge tube inside is actually, it's vibration resistant. They'll actually pipe it in such a way to where the motor, as it turns and stuff, will not break that tube internally. Now, as you kind of take a look at some of the other features, you know, you've got some valves in the head, you've got pistons and rods, and you've got some bearings again. As you take a look at that, you've got oil in the bottom and bearings. You've got some internal springs on the reciprocating compressor. So it'll set here, it actually has its own internal dampening, if you will, because it has some springs inside that'll actually help keep that compressor quiet and to keep the vibration down. And that whole suction area, that whole can itself, that whole, what we call the shell, actually acts as a muffler, a suction muffler. We have a motor overload. We've got a motor in there. We've got some windings. We got an internal discharge muffler to keep the sound down. We have a suction muffler to keep the sound under control, and so on. So there's a lot of components in there. But the main thing about the recip that we want to remember is the fact that you've got, it's very much like a car. You've got a crankshaft and a connecting rod and a piston and those components that make all that work as that piston moves up and down in that cylinder. So this technology is probably the oldest technology when it comes to compressor design and compressor manufacture. It's very easy to manufacture. It doesn't take a lot of real high-tech machining to do it. And the technology has been around a long time and is very, very reliable technology. So the strengths of a recip compressor, variable compression ratio, which means it's going to operate well over a wide range of conditions of outdoor temperature and indoor temperature. And the old recip compressors are just they're very bulletproof. They're very, very robust with respect to contaminants and compression ratios, has very low vibration typically because of those internal springs. Very simple to manufacture. Doesn't take a lot of real high-tech equipment to do it. You're able to control your quality very easily because, again, it's just cylinders and pistons, and technology has been around a long time. And again, very, very reliable, especially in off-design conditions. What I'm trying to say with that, so if you've got a situation where you've got maybe a mismatch, you've got a brand X coil inside, or you've got another manufacturer's coil inside, and a recip compressor outside and a condensing unit, they work very, very well in those off-design conditions. Now, some of the considerations, the sound levels may be a little higher, especially in the higher tonnages, because you've got that piston moving up and down, and those peak pulsations on that compressor as you compress that refrigerant can be a little higher depending on your conditions. In addition, unlike the scroll that is continually making that that high volumetric efficiency that we talked about, there is going to be some re-expansion. So I want you to think about this, team. When that piston comes all the way up, when it's squeezing that refrigerant up there, it's what we call re-expansion of refrigerant at the top of the compression stroke. What happens, that piston cannot go all the way to the very top, otherwise it's slammed through the top of the head, right? So there's always going to be a little bit of space at the top of that piston in that cylinder on a recip compressor. And so what happens is you squeeze that refrigerant up there, you're going to not let that piston go all the way to the top, otherwise it's slammed through the top of the head, right? So there's going to be a little bit of space in there. Well, inside that space, there's going to be refrigerant. And as that piston starts coming back down, that refrigerant that you just got done compressing is going to re-expand because you haven't got rid of it, right? And so re-expansion of that refrigerant does reduce efficiency on a recip compressor. That's really the only downside of a recip, is the fact that it's not quite as efficient. It's still going to be into the low 90s, whereas the scroll compressor is going to be into the mid to high 90% efficiency. But a recip compressor, is going to be more into the low 90s because of that, because you're doing work to expand that or to squeeze that refrigerant, but then you're going to turn right around and let it re-expand in the cylinder, because you got to have some kind of clearance in that piston. Otherwise, you'd be slamming that piston into the top of the head, and you can't do that. In addition, it does require hard start kits if the system does not equalize in the off cycle. So if you don't have a bleed port expansion valve, or a piston on the indoor coil, what's going to happen, you're going to need a hard start kit just because of the design of the compressor. So those are some considerations, but they're, when you look at the reliability and the simplicity of the recip compressor, I think most of the time that pretty much outweighs, the need for a hard start kit and some other considerations. Any questions or comments on that, Emily, that you can think of on the old recip compressor?
So oftentimes these really do well in some of our lower tonnages, correct?
Yes. As a matter of fact, one of the things I'd like to point out, is the fact, reciprocating compressors, they can continue to perform very, very well to other technologies, especially when you consider all the things we talked about. They're robust and they're, fairly low vibration and easy to manufacture. And in those lower tonnages, typically the 1.5 to 2 ton, really up to about a 3 or 3.5 ton unit, depending on the SEER rating and, and all the different considerations when you're designing something. But really the sweet spot for a recip is about 1.5 to 3 tons, up to about 3 tons, but really 1.5 to 3 tons. Recips still do very, very well when you look at the motor technologies and the cost and the manufacturing, of it. They're very, very, they're just, like I said, it's old technology, but it's good technology, and they still work very, very well. Good.
All right. I don't see any questions in the chat box.
Okay, well, let's talk a little bit about the rotary compressor. So as you take a look at that graphic, you can kind of see the rotary compressor. Again, it's almost like a cam inside that's kind of rotating around inside of a cylinder. And as that cam rotates, it kind of squeezes it as it moves it towards the side of that housing. And so that rotary compressor is a little different technology, but as you kind of look at the animation a little bit on the left-hand side, you can kind of visualize how that refrigerant comes through. That offset cam in the middle, or that rotor in the middle is offset, kind of squeezes it as it moves it to the side. And again, just like before, we do have a suction port. Remember, every compressor has to have a suction port and a discharge port. And we've got a discharge port. Now, on the rotary compressor, the entire shell on the rotary is high side. So that's interesting. It's exactly opposite of some of the other technologies we've looked at so far. So the entire shell is the high side on a rotary. And the suction accumulator itself, where the refrigerant comes in, that cool suction vapor comes in. Oh, and by the way, as a little side note, the reason we have a suction accumulator on any product team is to ensure we don't have liquid refrigerant slugging back to the compressor. So the reason the suction accumulator there is kind of a holding tank, if you will, that allows that refrigerant to boil off in that accumulator in case we get a little bit of liquid going back to the compressor. We want to make sure we handle that liquid and we boil that liquid off in the suction accumulator into a cool vapor. That way we don't have liquid slugging back into that compressor and possibly causing damage. Now remember, team, the number one cause of liquid slugging back from the evaporator is low airflow, filthy air filter. So keep those coils clean, make sure you got the right airflow, and make sure you've got a clean filter in there, and you should never have any problems with liquid slugging going back to your compressor. So back to the rotary compressor. The entire shell is the high side, and the suction accumulator is the low side on the rotary compressor. As we take a look at some of the key components, you'll see that accumulator acts as a liquid separator and a muffler. On the very bottom of that compressor, just like we had before, team, we've got oil pickup, and we have a bearing down there sitting there in oil. We've got some rotors and vanes inside that rotary compressor. We've got a motor to drive it. We've got an oil separator in there just so you don't push a lot of oil out the discharge line into the refrigeration circuit. We've got some overloads in there for motor protection and so on. Go ahead. Did you have a question?
Oh, I think they muted themselves again.
Okay. Emily, do you have any questions or comments on the basic operation of rotary?
Yeah, so I see it's got oil separator in there. Another thought that came to mind is, sometimes there's different types of oils based on your refrigerant. Is it based on compressor, refrigerant? What are kind of some of the considerations?
That's a really fantastic question. So the type of oil that we use in any compressor technology is going to be largely based on the type of refrigerant. And so the basic types of oils that we have mineral oil, which you'd find on the old R22 systems. We have what we call alkyl benzene oil, which was kind of a hybrid oil that was good for some of the alternate refrigerants, especially in the commercial refrigeration world. You'd see alkyl benzene oil. And then we have what we call polyol ester oil. Polyol ester oil is a pure synthetic oil, and it predominantly is going to be used with any of your 400 series refrigerants is typically where you'll see it. So like 410A, 407C, and so on. Those would all have a polyol ester oil. It's a very, very clear oil. It's a very high quality synthetic oil. Now, please write this down or keep note of this. Even though it's it's a great oil, it is hygroscopic. Now, what that means is it does absorb moisture. So on a 410A system, you open that system up, you want to make sure and keep it really clean and dry. Open that system up, because that polyol ester oil will absorb moisture to the tune of about 10 times greater than the old mineral oil that we used to see in R22. So keep it clean and keep it dry if you're going to be servicing the equipment, and when you install it, don't forget to use that nitrogen when you braze those lines up and get a good deep evacuation. down to 500 microns or less is recommended, so we don't get any moisture in that oil or in that system. Good. Okay, any other good questions or comments?
I know we had a few people that were unmuted. I went ahead and muted them, but feel free if you have a question to unmute yourself now at this time and let us know if you have any questions. All right, go ahead, Joel.
Okay, well, let's look at some considerations and strengths. Some of the strengths of the rotary compressor is a variable compression ratio, and it operates well over a wide range of conditions, and it is well suited for inverter drive systems. As a matter of fact, you're going to notice that like on our Hisense, our HMH7, for instance, it's going to have a rotary type of compressor on that inverter drive. So it does lend itself well for those inverter drive technologies. They are small and lightweight compared to some other compressor technologies. And historically, they've had a design advantage in your small self-contained applications. So, you know, window units and small units and mini splits and stuff like that, you'll see that they'll have a rotary compressor typically is what they'll utilize in that technology. Twin rotor designs offer lower vibration levels and higher efficiency across some of those bigger tonnages. For instance, if you have like a 5-ton or a 4-ton mini split, you're probably gonna have a twin rotor type of design. Now, some of the considerations with the rotary compressor, they do have very close tolerances in it, and it does require strainers and accumulators and different technologies to help control any contaminants that are in that system. Now, they may be less efficient than other technologies, but that inverter drive is going to help improve that efficiency. So again, it lends itself well to inverter drive technology over other compressor technologies. The vibration levels of a single rotor design may be a little higher than like your twin rotor design. So, you know, based on the tonnage and the size of the unit, you may have 1 or 2 rotors in there. But a lot of times, again, you'll see that on inverter drive, mini splits, those types of technologies, you'll see the rotary is the preferred compressor technology. Some things to kind of remember too, twin rotaries are widely used in Asia in the 3 to 5 ton air conditioners and heat pumps. And frankly, improvements in compressor technology over the years and so on provides efficiencies comparable now to other technologies, especially when you start getting into inverter drive. So we get some very, very nice SEER rating, especially with the inverter drive technologies that we're using. So rotary compressors. Any questions or comments on them?
Don't see anything in the chat, but is there any times where we would see an accumulator other than on a compressor?
Well, the only time you'll see it, you know, like separate from a compressor is if it's designed that way. Some products don't have accumulators, obviously. You'll see accumulators typically on heat pump products because during the defrost cycle, we can have a tendency to slug some refrigerant back. So heat pumps typically will have accumulators on them for that reason, to help manage that slugging. Typically on straight cooling units, a lot of times you don't see accumulators, but on the rotary, it actually has that built in. It's actually part of the rotary technology to have that accumulator on, because that accumulator is the low side of the rotary compressor.
And I think even in some long line applications, I think our TCHD, that one was really well designed for some of those longer line sets, and it had a built-in accumulator.
Yeah, so basically, anytime you start getting above about 70 to 80 feet, it may be even on straight cooling, to your point, Emily, on straight cooling application. If you have a line set longer than about 70 to 80 feet, it may require a suction accumulator as a add-on or as an accessory to consider on a long line length application. That is correct.
Or what about vertical rise? Does that have anything to do with it?
The big thing about vertical rise is going to be the amount of refrigerant let's say if the condenser is setting on the ground and you have a high vertical rise, typically what we'll do is we'll have other technologies like solenoids or check valves in the liquid line to help manage that, because what can happen if you think about it, refrigerant is about 1.5 times the weight of water. And so if I've got 50 feet or 60 feet of liquid in a liquid line going up a wall, the compressor's got to overcome that. And so based on how long it is and how high it is and the tonnage of the unit and so on, there may be some considerations as far as hard start kits or solenoids in that liquid line and so on, which would be like a special type of application. But yeah, high lift applications can be a consideration based on your compressor technology, but also based on your job site application as well. That is correct. Good questions.
Haven't seen anything come into the chat yet either, but feel free to type into the chat or unmute yourself as well.
So the burning question I always like to ask, and that I like to pose is a single compressor technology the best for every application? And so we know at Johnson Controls, through rigorous testing and rigorous application and all the different things we do, at Johnson Controls, we choose the best compressor technology based on testing and application. Now, unlike our competitors who may choose to apply one compressor style across their entire product range. So not beating up on anybody, but the fact is what we do, we believe that we set the industry standard as far as application and training and all the different things that we do and testing and our HALT facility. We know it's important to choose the best compressor based on the technology that we have as far as SEER rating and application and all the different things. So we don't just take one compressor technology and try to squeeze it into all applications, because we know that there is no one best compressor for everything. And so that's one of the things that we're very proud of here at Johnson Controls. We look at all technologies and choose the ones that best apply for the platform that we're designing. And then I just wanted to talk a little bit about our HALT facility. So we can see on the left-hand side, we've got, and on the right-hand side too, some extreme weather testing. We see that, we're going to do a 5-year life cycle test in 4 months, going from 125 all the way down to -10 degrees. And, there's 29 reliability tests, 442 total test points in our highly accelerated life test cells, what we call the HALT facility. As you can see, we really torture these things and when we do our testing on these things. So because we are constantly evaluating all current compressor technologies, and we do not force one type of compressor to fit in every application, we know that all designs have to meet the same high quality of reliability and all the standards of reliability. Unit warranty coverage is not dependent, and I'd like to stress this, unit warranty is not dependent on compressor technology. It doesn't matter what kind of compressor you have in your unit. With registration, we're going to have a 10-year part placement on that thing. So whether it's a scroll, a recip, or rotary compressor, with registration, they're all going to carry the exact same warranty. And if you find whatever type of compressor technology you find in your champion product outside, it's been thoroughly tested and thoroughly vetted, and full warranty on that compressor, regardless of the technology that you see out there. And again, just to kind of, wrap up the reliability part of it, we've got those test facilities in Norman and Wichita and Milwaukee, and we use rigorous use of statistical and design tools to ensure that high quality. We continually improve, and we get involved with our supplier qualification and component evaluation, and we continually evaluate and warranty coverage. One more time, warranty coverage is not based on the compressor technology. So, when you buy that champion equipment, that every compressor that we use in regardless of the platform out there, has gone through the same type of testing and vetting and reliability testing, and carries the exact same warranty. So at this time, let's go ahead and open the floor up. If there's any questions about our compressor story today, feel free at this time to go ahead and unmute your mic, and we'll go ahead and take those questions today, Emily, as we kind of start heading towards the conclusion of our training today.
Yes, so feel free to reach out if you have any. So Joel, we kind of talked and based on history a little bit. You know, what are some of the considerations? It sounds like, you know, in the past people really shied away from one compressor type to the other. But they've obviously, just like Johnson Controls, has continued to test and get better. What are some of the things to say when you might have a customer that comes up against a certain compressor type?
That's an interesting observation and question, Emily. So I find that in our industry, and I've been in this industry a long time, I find in our industry sometimes opinions are kind of based on they could be on a particular experience, a bad experience or a good experience. It may be a homeowner's perception of one particular compressor, you know, in an older piece of equipment sounded different than the new one. So there's just so many factors to answer that question. But I think the real simple answer is people just formulate and they have opinions on what they like or they don't like. But if you really start digging into the data and digging into the science and digging into the application, all compressors don't fit into just one box. And so based on your application and your platform and your SEER rating and what you're trying to achieve and cost and sound and all the different things, if you really dig into the science, we use the best compressor, you know, and the best technology for any particular platform. And I think opinions vary on that, but the truth about it is, I think when you really start digging into why people think they don't like a particular compressor technology, more often than not, if you start digging in, they really can't tell you why.
Very good. We do have another question that came in. So what's the first question to ask when a contractor believes they have a bad compressor?
Oh, that's a good question. So what I normally do is if you, first and foremost, let me set the stage for that question. Depending on what manufacturer you talk to, us included, some 60 to 80% of all compressors that go back to the manufacturer for warranty, there's nothing wrong with them. And so they're being misdiagnosed. So as an industry, we misdiagnose a lot of compressors. And so on heat pumps, if you think that compressor is not pumping for whatever reason, chances are it's something other than the compressor, like an expansion valve or a reversing valve is leaking, are more than likely. On a straight cooling unit, if that compressor is not pumping or it's not starting, there's a really good chance that the run capacitor is bad or there's some electrical component that's keeping that thing from working properly. So compressors typically don't go bad, they're murdered, so to speak. That's what Bruce Porter likes to say. You know, compressors don't go bad, they're murdered. And what'll kill a compressor quicker than anything else is low charge and not getting that cool gas back to the compressor like we talked about, and mischarging and those types of things. So as long as you keep the system clean and keep it dry and evacuate it when you do your installs and charge it properly and give me the right airflow, they're going to work well.
Very good. Any other questions? You can feel free to unmute if you have one that you'd like to speak. I think we covered quite a range here, Joel. I know we did not get our next calendar date out there, but we do plan to have another calendar date in July.
Okay.
Do you want to speak to what we discussed on our next content?
Well, to be honest, I'm going to have to plead a little ignorance because I don't remember what we were going to do next. I know basic refrigeration cycle, the compressor story, and what was our next subject? Help me out.
The next, we were going to dive into components a little bit more.
Okay. So and as its name implies, we'll start breaking down some different sessions. We'll decide what we're going to do specifically, but whether it's expansion valves, reversing valves, you know, different components that make up a refrigeration cycle and you know, an air conditioning system as a whole. But by all means, yeah, I look forward to training with everyone again.
We will be sharing this recording for you guys as well. And will the next refrigerant used, will use a different compressor technology?
Oh, that's a great question. No. So what we're going to see is, the compressor, the motors may change a little bit. They may have a little different bearing design or something because of the different oils or what have you. But the basic compressor technologies are going to stay the same regardless of the refrigerant we use, whether it's, and if you think back, whether it's 407C, 410A, R22, back in the old days of R12 and so on, the compressor technologies have stayed the same. We've had to change the oil. We've had to make some modifications to motors and stuff internally, for some higher pressures and stuff like that. But the same technologies will be prevalent regardless of the refrigerant that we use. You'll have a recip, you'll have a scroll, or you'll have a rotary compressor will be the technologies that we're going to see.
So technologies will probably be staying the same, but we might have different models based on the different units to help get that even more higher efficiency that we're going to have to see for SEER 2.
Absolutely.
As well as the next refrigerant.
Absolutely. I think we're going to see a lot more inverter drive technologies, come down in different SEER platforms, because it's a great way to get a higher SEER rating, but also gives you better reliability and so on with some of those inverter drive technologies.
I see, Bob, you've got your hand raised. Feel free to unmute yourself and ask your question.
Can you explain SEER 2?
Emily, go ahead. I'll let you take a stab at that one.
All right, certainly. So it's basically a different way that they're testing the equipment. And if you look into some of the details, it's basically, if we're comparing SEER to SEER 2, your typical 13 SEER equipment's now going to have to be about 14 SEER to hit that SEER 2 requirement. So it might not look like we're really changing much. Our entry level, 13.8 SEER 2 or 13.4 SEER 2. But on the backside, being able to test it, they have to, it's, I think, about 0.7 SEER to hit that next level.
And in addition, one of the things that's actually, in my view, a good news story is on the SEER 2 testing. One of the requirements is going to be a higher static pressure on the airflow. And so from a practical standpoint, you're not going to see in the field, if you just go out to, Mrs. Jones's house or Mr. Smith's house in the field right now, the typical homeowner, their airflow is not going to be very close to what we actually test at currently. So SEER 2 is actually driving manufacturers, us included, to test at 0.5 inches of total static pressure on the airflow, whereas before that was not required. So
it was required, Joel. Unfortunately, though, it was closer to 0.2 to 0.3 static.
0.3.
That was what was based on HRI standards, or I'm not sure if it probably wasn't HRI standards. It was it's based on the standards that we have to test by. But now it's gone up, which is, like you said, Joel, more realistic.
I think so.
Of what we're going to see. Great question, Bob. Thank you.
Good questions.
So, and then Joel, there was a few thank yous for putting this together. Great information. So if you guys do have any recommendations on any HVAC basics that you would like to talk to in the future, feel free to shoot Joel or I your message, and we look forward to having you guys next time.
Absolutely. Thank you. And Emily, I'll look forward to that, to the video, and we'll get it posted out there on the YouTube training channel once we get that video downloaded and stuff. So be looking for it out there on the YouTube training channel, and it'll be called HVAC Basics, the Compressor Story.
All right. Thank you, everyone.
Thank you. Have a good day.